welcome everyone. This is our fourth meeting of talk for the year, and we have Professor Zurab Janelidze today, and he's been a professor for quite a while now at Stellenbosch University. And for those of you who do not know him, he has quite I think I can call it an unconventional way of teaching mathematics. He tries to get a bit away of the maybe computational and memorization of mathematics to more creative and explorative way of doing mathematics. You'll most certainly always start with that mathematics is for the love and understanding of the subject. So yeah, that's quite a present theme in his way of doing stuff. And yeah, we are privileged to have you here, Professor.
Are you? Rocco, thank you so much. This was a lovely introduction. I'm very much humbled. Can you see my screen?
Yes, we can.
Okay, so the title of the talk is Partial Symmetry. And we're going to look into a subject that I myself discovered very recently. So this is actually a joint work with Dr. Francois van Niekerk and our joint student Jade Viljoen, who did honors project with us last year. This year she's becoming a teacher. She's already teaching at a school. And so somehow we went on as you say, the creative path, and we came up with some topics which on one hand seemed to be very basic, but on the other hand didn't seem to receive that much attention in the literature. And then the process never stopped, and we explored, and of course on the way we found many links with very well-known things. And yeah, so that's the background. We are actually trying to finish this paper this month, and also we're working a bit last month as well. Okay, so what is symmetry? When we have a symmetric picture, for example, I think this program has some symmetric shapes here. Let's take a star. I don't like this star because it reminds me of a communist star, and I'm from Soviet Union, where the star was used for killing many people. So let me use a different shape. Let me use this star instead. Okay, so when we look at a shape like this, we see symmetry in it, right? And the question is, what is this feeling of symmetry that we have? And it turns out that we can actually mathematically describe what's happening there. In order for the mathematical description to be not too complicated, we can consider a discrete version of the picture. For example, we could consider a shape consisting of 4 points and another point in the center, and arrows going like that. And then a symmetry is nothing other than a permutation of these 5 points, which preserves the arrows. So, for example, if you swap around these 2 points, right, but keep these ones, then somehow on the picture that corresponds to us identifying that this portion of the star is similar to that portion, but maybe we don't want to deform the star like that. If we swap them around, then the shape, we'll have to break the shape, right? So we might want to add some more structure to this discrete version in order to not allow such things. For example, if we add arrows like this, then we will no longer be able to swap these two around, because there is an arrow moving, going from this vertex to that vertex. But if I now move that vertex here, there is no longer an arrow going from this vertex to that vertex. And so this permutation is not going to preserve the arrows anymore. We have an arrow when we start out, but then we lose this arrow when we arrive to the destination. So this way you can take a beautiful symmetric picture and discretize it like that, eventually coming to a model where the symmetries of this discrete picture will correspond to the symmetries of the original one. Okay, so all this is very well known, and when we look at already when we look at permutations of a set, what we observe is that if you've got a function f from a set to itself, and if this function is a bijection, let me remind you what it means for a function to be a bijection. So it means that first of all, it's injective. If f of x is equal to f of y, then x is equal to y, and that holds for every x and y in the set. And then also it's surjective, meaning that, okay, let me put this for all x and y here. It's surjective, meaning that for every y, there exists an x such that f of x is equal to y. And if your set is finite, so if I draw the finite set like this, and I draw two copies of it to display how the mapping works. When the mapping is a bijection or a permutation, what will happen is that now these are different kinds of arrows. These tell us what is mapped where by the bijection. What will happen is that, we will get a one-to-one correspondence between the left side and the right side. Now, if we have two such things, like functions in calculus, we can compose them, right? We can have a function y equals 2x and a function y equals sine x, and we can compose them, and we get a function sine 2x. If we compose them one way around, the other way we'll get 2 sine x, right? And so general functions can also be composed. And when we're composing symmetries, it's something meaningful because we get another symmetry as a result. And eventually we get a mathematical structure called a group, which describes to you somehow the mathematical content of symmetry. So for instance, just to give you a very simple example, if we take only 2 points, if we take just 2 points, and we ask ourselves, okay, what are possible symmetries we can find on the set of 2 points? Now I'm drawing them separately because I want to view a symmetry as a function. So we're looking for one-to-one functions, and here is one. This is the identity function, and the other one is this, the one that twists things around. And let's call this I for being identity, nothing to do with the complex number I. And let's call this J for, or maybe T for twisting. And now a question to, by the way, I noticed some of my colleagues are in the audience. Thank you for coming. Do we have also first-year students in the audience? Rocco, you should be able to help me with that.
I am not sure everyone, that joined, Professor. I don't know everyone.
Okay.
But there seems to be no student number above, I think, 24. So maybe then there's no first-year students yet.
Yeah, because I don't want to say things which are completely trivial to everyone. So So let me make a test. So I'm going to ask a very trivial question, and I would like to invite anyone for whom this question is not completely trivial to answer, and then I will know that I can ask such trivial questions. What do you think we will get if we compose T with itself? Okay, maybe let's move now from first year to second year. Maybe a second year student can answer this. How about you, Rocco? What do you think we will get if we compose T with itself?
Well, if T is twisted and you compose it with itself, doesn't it twist back then?
Yes, and so do we get I or do we get T?
Yeah.
Or do we get something new?
I thought we would get I, but I didn't. Yeah, just.
Yeah, I also think like that. I also think we will get I. And it's of course very easy to confirm this. If geometric thinking doesn't help us, then we can label these points, and then we can compute the values of the composite to match with those of the identity map. So the group we get here consists of these two elements, the identity map and the twisting. And the operation, so every group has a binary operation on it. And so the operation in this case is the composition. And there needs to be also an identity element in the group. And so that's given by the permutation I. And there also needs to be inverses in a group. So for every element, there needs to be another one whose composite with that one is the identity. And so for T, it's itself. But for I, it's I, right? Because I composed with I is clearly I. And so we have inverses as well. And then we also need associativity law. In general, it states that A composed with B composed with C equals A composed with B composed with C. And this we get for free because in general, composition of functions, even if they're not permutations, is associative. And we get something called a group. So that's what a group is. I basically described to you now what a general group is. Okay, so what to do next? Well, you open doors to a beautiful area of mathematics called group theory. And like every other area of mathematics, it has some beautiful results. There are very complicated problems that takes many years, and some of them are still unsolved. And it links up very intimately with lots of different areas of mathematics. And so there we go. We get a very genuine piece of mathematics out of exploration of symmetry. Now, what is partial symmetry? So going back here, before we inserted these arrows, remember we said that we want to swap around these two because we see that sorry, I'm using the wrong, yeah, these two, because we see that they kind of match. So this portion of the star, right, can be matched with this portion of the star, right? And if we keep the others fixed, then we can't do that unless we destroy the star. But we actually don't want to think of the others at all. We just want to concentrate on those portions. And so this is the idea for partial symmetry. Now, if I look at the picture that was used to design this beautiful advertisement for the talk, so whoever designed this well done. So you can see this picture here in the background. It has lots of symmetries, and it also has lots of partial symmetries, right? For instance, some of these orange lines perhaps match with some of those here, and so on. Or maybe it's actually not so easy to identify partial symmetries here. It's actually not clear if the whole thing is symmetric or not. It seems to have very, very minor asymmetries, which might be destroying the symmetry. Anyhow, so now the question is, what mathematical structure do we get by studying partial symmetry? So if looking at symmetry, we get the notion of a group, what do we get if we want to look at partial symmetry? And so let's try to explore this question a bit. Okay. So let's take a certain shape. Maybe we will stick to that star. Or actually, let's take a cycle this time. So let's take a directed graph of this kind. And let's try to understand the structure of partial symmetries of this thing. And maybe we can discover some mathematical structure that can describe this phenomenon in a similar way as group describes the phenomenon of symmetry. Okay, so let's pick one partial symmetry. For example, we can match this. Okay, maybe that's too simple. So let's take this part. We can match this with, so the orange part can be matched with this one. And that's definitely one of the partial symmetries, right? So let's denote that partial symmetry by some letter. Let's call it X. Okay, so what about the identity map, the one we had before, the I? We have I as well here, right? Because we can match everything to itself, and then we get the map I. And it will be true that X composed with I will equal X, and it will also equal X composed with I on the other side. So we still have this identity law for composition of partial symmetries. Do we have inverses? Okay, associativity we have again, although maybe it is a bit less clear. Actually, we should describe what composition will be first. So let's say this is X, the one that I've drawn here, and now let me draw another partial symmetry, and we will call it Y, and then we will want to compute what will be the composite of the two. So to do that, I'm going to draw another copy of this picture, and let's label this. So 1, 2, 3, 4, 5, 6, 7. And here we have as well 1, 2, 3, 4, 5, 6, 7. And the partial symmetry X, what it does is the following. So it maps, we have 1, 2, 3, 4, 5, 6, 7 on this side as well. So it maps 7 to 3, right? Maps 7 to 3, and it maps 1 to 4, and it maps 2 to 5. Yes? So I should keep these arrows here as well. And now imagine we have another partial symmetry which does the following. So we draw another copy of this cycle. And maybe you can tell me, someone in the audience could suggest to me what this other partial symmetry should do. And I'm going to draw that with a different color, with green. Would anyone like to suggest what the other one should do?
Maybe 2 goes to 6 and 3 goes to 7.
2 goes to, thank you so much, Leslie. 2 goes to 6 and 3 goes to 7. This will be a partial symmetry indeed, because the arrow is preserved and the function is injective. Okay, now what happens when we compose these two partial symmetries? Well, first of all, can we compose? It feels like the codomain of the one doesn't match with the domain of the other. But now these are not functions anymore, these are partial functions, you see. And so to compose them, what we will do is the following. First of all, let's clarify for us the domain in the range of the partial symmetries. So that's in the first case, and in the second case we have that being matched with this. And so when we compose, what we do is we in the middle object here, we overlap the two pictures. In this case, unfortunately, the overlap is very tiny, it just consists of one point. And then we restrict the partial symmetry on that point on both sides correspondingly. So here it will be just this one, and on that side it will be just that one. And so then we define the composite of these two partial symmetries to be the matching of the yellow parts from the first picture to the last picture. So when you compose partial symmetries, things shrink sometimes, right? Because of the fact that these functions are not surjective. Okay, so things shrink, but we can still compose them. And in fact, it's not difficult to see that this composition will be associative. So we've got the associative composition, we've got the identity law. What we need to get a group are inverses. And the question is whether we have inverses or not. So what do you think we should consider as a possible inverse for X? So X is the partial symmetry that matches this orange one with the blue one. What would be a natural candidate for an inverse of X? Any thoughts on this? So what is an inverse? We want something that composed with X is going to give us I. Do you think we have such a partial symmetry? Or we don't, maybe? It will be a pity if we don't. It means we don't get a group anymore, right? Any suggestions?
Maybe map them backwards, like
sure.
3 to 7 or something like that.
Yeah, thanks. I mean, isn't that the most natural thing to consider, to map them backwards? The problem, though, is that when we do map them backwards, this can no way enlarge the domain of X, right? So when we compose X and its inverse, we will not get I, we will get a restriction of I. We will get the following. So this is 1, 2, 3, 4, 5, 6, and 7. So we will get a partial symmetry that matches this thing onto itself. And that's not the same as I, which matches everything onto itself. So unfortunately, we don't have, well, I mean, this is not a proof yet, but one can actually prove that we don't have inverses in this monoid. So when a group doesn't have inverses, it's called a monoid. But still, there is something beautiful about the thing that Mr. Buchner just proposed. It kind of feels that it should be still called an inverse of X. But then, if X composed with X inverse is not equal to I, then what mathematical property should be used instead of this usual inverse law to identify X minus 1 among all the other partial symmetries in relation to X? So can we come up with another equality? This one fails, unfortunately. Can we come up with another equality that can be used to define this different notion of inverse? Okay, so now this is getting a bit more complicated. So I would be quite surprised if any of the students will be able to answer this question immediately, unless you've thought about it before. Can you tell me an identity here that will be similar to this one, but not the same because this one fails, which can be used to define this type of inverse. So when you try to make something work and it doesn't work, what do? You continue working, right? You don't give up. So we composed x with the inverse of x and it didn't equal I. So let's continue composing. Now, what can we compose this with? Maybe there we can get an answer. So what possible things can be composed with this composite? I mean, we might just compose it with something completely randomly different, but that would probably be not very useful, right? So shall we compose it again with, well, if we compose it with x minus 1 again, then we will run into trouble. We will get empty match because now the domain and codomain of this is just yellow part, and x minus 1 has a domain, the blue part. And when we set up a picture like this for composition, because the yellow part and the blue part do not intersect, the partial symmetry will vanish. We will get a partial symmetry, which is the empty map. It still counts as partial symmetry, but we will completely destroy our expression. And we don't want to do that. So we don't compose with x minus 1, and so maybe we compose with x. Okay, now could someone tell me what do we get when we compose this thing with x?
We get x.
We get x, yes. We quite remarkably get x, as if this was identity. If it was identity composed with x would be x, but it's not. But still, this composite gives us x. And okay, so there is a subject called semigroup theory, which studies semigroups. So what are semigroups? Take a group, remove from it the identity element, and remove from it the inverses. Then what you get is called a semigroup. And a semigroup in which every x has this companion, which in semigroup theory is called inverse, that satisfies this rule, and also the other one with starting with x minus 1 and then x and x minus 1 equal x minus 1. So such a semigroup, where for every x this thing exists, is called an inverse semigroup. Okay. Now, in group theory, you can ask which groups are those that come out as permutation groups of a finite set. So this is kind of original motivation for notion of a group, right? Although every group embeds into a permutation group, that's a different story. I'm asking something slightly different. I actually want to recover the set whose permutation group this is. And maybe Professor Van Veek knows the answer to this. I don't. I've never thought of this question either. But I thought of a similar question for semigroups. So which inverse semigroups are those that come out to be semigroups of partial symmetries of a directed graph? And then I couldn't find anything in the literature. And then I emailed a colleague in Hungary, Professor Laszlo Marki, asking him whether he knows any reference. I told him, look, this is a very easy question to solve. I just want a reference because I want to cite it in my paper. And he emailed one of the top experts in semigroup theory. And before her email got back, I also found a paper by her and co-authors written last year, where they characterize, where they answer this problem for the first time in the literature of semigroup theory. This is quite surprising and quite remarkable. So with our honors student, we were working on this in November last year, and that's exactly the time when that paper was published. But their answer is slightly more general, in a slightly more general context, not exactly this question. So we actually had a correspondence where we formulated this answer through the emails. Okay, but that's not what I would like to tell you today. So this was just one part of the story of partial symmetries, which leads to the notion of a semigroup. And with my childish exploration of this, I mean, I found out about this concept. I mean, I knew about this from talks and so on, but I've never really carefully thought about it. So I rediscovered this in January, not in January, sorry, in February. And then I found out, okay, this is all very well known, and I was very happy to see that things have been done around these things. And the subject of semigroup theory is very beautiful, by the way, because, for example, another very interesting question, this thing that we got here, right, the yellow part, when we compose X with its inverse. So matching a part of your structure with itself. These types of symmetries can also be characterized inside the semigroup of all symmetries, and they are nothing other than the idempotents. So they are those partial symmetries G, such that the G composed with G is equal to G. And if you think about it, you'll see why this should actually be so. And so a lot of things about partial symmetries of a directed graph can actually be captured purely algebraically using equations involving compositions and well, inverses in the sense of semigroup theory. Okay, so but we're not going to go into that subject. What we're going to do instead, I'm going to share with you some of the insights I got from the further development that followed that honors project I mentioned. So since the topic of investigation of partial symmetries of directed graphs seems to be quite natural, but at the same time new, we asked very basic questions. For example, if you take the same cycle we had before, right? If we take the same cycle, we can ask the following question. How many partial symmetries are there for this cycle? And of course, this is a cycle of size n, 7. And we want to answer this question for a general n. Counting basic transformations of discrete structures is not a new topic in combinatorics. And in the beginning, most of these questions can be very easily answered through some very basic experience in the subject. But then when you slightly advance your questions, suddenly you might get something very, very difficult. So what we got was something kind of intermediate. We got something on which we had to work for some time. So the student couldn't solve this problem. She formulated this as an open question. Then Francois van Niekerk solved the problem, but when I looked at his solution, the formula was correct, but the proof was wrong. Then I had an attempt on it, and I worked for quite a few hours on different days, and I couldn't prove it. Eventually, I got the proof. And then he told me that he actually also had a different proof that was correct. But along the way, we came across something quite interesting that leads us to Pascal triangles. So I want to share this with you now. I'm just trying to open the draft version of the paper we're working on. In the meantime, by the way, if you have any questions, please do ask. Okay, so this is how the paper is called. It's still work in progress. We call this thing endomatch index of a directed graph. The number of partial symmetries, which we call matches, according to the terminology we used last year, because we're matching a portion of a graph with itself. And so the endomatch index is the number of ways you can match a portion of a directed graph with itself. And now I'm going to show you how many partial symmetries does this cycle have, but maybe you can make an estimated guess. Would anyone like to try to estimate how many there will be?
Maybe 7.
7?
Like 1,000-ish.
Okay, so I see now that in the paper we only got a table up to 6. So if there were 6 vertices instead of 7, there are 571. And the general formula for counting this for a general n is the following. So this is the formula. And I think I'm going to now disappoint Rocco, who said I don't like computation, because there was some computation involved to get this formula. By the way, since this paper is still work in progress, it might happen that eventually we will simplify some formulas. So far, we couldn't simplify this one further. And so you see what this formula tells us. So ignore the other 2 formulas. I'm not going to talk about them today. So this is the cycle digraph. And for each n, which is the number of vertices, we now have the number of partial symmetries given by this formula. Now you might think, why do we need a formula when we have computers? So let's code into a computer to count how many partial symmetries there are. Well, I tried using Python language, and when you do that, when your n becomes bigger, the computer takes much long time to do because of all the permutations involved there. So it's an exponential thing. But now with the formula, it's much quicker. So even though there are computers, the formula is still useful. But of course, mathematically, it's also interesting to see what the formula is. Okay, now the interesting mathematics that came out from this formula was the following. So I'm going to show you the strategy we used to count these, which is due to Francois. So the first thing you want to count is how many portions you can isolate in a cycle. And so the difficult thing is that you see, the structure of your portion determines how many matches of that specific portion has. So let me show you an example. So imagine we maybe yeah, okay, so imagine we take for instance this portion. Okay, now it's very easy to see how many ways we can match this with others, right? It's just it amounts to deciding where 7 is matched to, right? So you choose where you want to match 7, and the rest is automatic because of the direction of the cycle. But if you choose your portion that you want to match to be like that, where you got some disconnection between the 2 parts. So we want to match this blue thing, right? Then you see this can be matched in many different ways. And this also, and these 2 matchings are quite independent from each other, except that they can't overlap. We can't match both to the same place because then it will not be an injective function, right? So depending on how many, this is called connected component, how many connected components your portion of the graph has. So now we can't fit anymore, because if I do this, then it should be connected rather with that one. That will determine what is the specific number for that type of portion. And so that this is why we get the summation. So in this formula, the I represents the number of elements inside the portion being matched, and J represents the number of connected components. So in this case of the blue area, the number of connected components is 2, because there are 2 pieces that are not connected to each other by a direct arrow from one vertex to the other. And so then it just amounts to counting, first of all, how many ways we can choose for a given I and J, how many ways we can choose such a blue portion. And once we know what the blue portion is, then how many ways we can match that with other similar portions. And so we end up having 2 things that need to be multiplied with each other. And then a calculation shows that this calculation here shows that when we multiply these things, things simplify. Okay, so what is interesting is just this first part. How many ways can we choose a portion of the cycle? And you might think that this would be a question that already has an answer, but apparently not. Let me show you how this can be interpreted in a slightly different way. Think of the cycle now rather as a polygon. Okay, there we go. Now I can encode a portion like this in this way. Whenever the arrow lies in the portion, I'm going to color the corresponding edge of the polygon. So these are 2 colored ones. And then whenever some vertices are skipped, I'm going to connect those edges with lines like that. Okay, so remember what I and J were. I was the number of elements in the blue area, which is 4 in this case, and J was the number of connected components, which was 2. So identifying this portion is then equivalent to identifying a polygon that's inscribed in the given polygon, right? Where J many edges, where they're all together I many vertices. So the 4 tells us how many vertices there are. So there are 4 of them, 1, 2, 3, 4. And let's see, how can we see? Yeah, and the number of edges that don't coincide with one of the edges of the given polygon, so these ones, the number of these will be exactly the same as the number of connected components. So that's what J tells us. So for example, if we set our J to be the same as I, so let's say I is 3 and J is 3. So what does that mean? So let's draw this polygon again. And now we want to identify 3 vertices that will be inside the blue area. But there also needs to be 3 connected components. So all these 3 vertices, none of them should be connected with an edge with each other, right? So one possibility is this. And so with making I and J equal to each other, we get triangles that are inscribed in a polygon. And of course, these specific numbers are known. It is well known how many ways you can inscribe a triangle in a polygon so that none of the edges of the triangle coincides with the edge of the polygon. Okay, so I want to show you now something we got there. So this is the last section of, sorry, there are a few other things before that. There we go. Okay, so these numbers are displayed here. So here is the I, and the j is equal to I in this case. And n is the number of vertices of the polygon. And we get these sequences. So when I is 1, we get this sequence by increasing n. When I is 2, we get that sequence, and so on and so forth. And what we see here on the right-hand side is the entry in something called Online Encyclopedia of Integer Sequences for these specific sequences. So up to I equals 6, the entries are there. For I equals 7, the entry is no longer there. But moreover, the interpretation in terms of these polygons I talked about is not mentioned there at all. And hence, the fact that this has something to do with partial symmetries of a cycle is also not known. I mean, that sequence we get there is also not in the encyclopedia. I'm going to show you in a moment how this encyclopedia looks like. But what I want to do before that is that you see that there's a bunch of zeros here in the beginning. And why is that? Because when I is too big, you simply can't fit anything with j being equal to I. For example, imagine you've got a polygon that has 4 vertices, right? And you want your I to be, let's say, 3, and you also want j to be 3. So that means choosing 3 vertices in such a way that when you connect them, none of the edges match, coincide with the edge of the polygon. But that's impossible, right? You will be forced. So the number of these things is 0. And so that's how we get these zeros here. So if now I look at this number 2's this way and 2, 3, 4, 5 increasing that way, and I twist this picture around, I get a triangle. And it turns out to be Pascal's triangle, except that we have 2's on the left diagonal, and so instead of 1's, right? And 2, 3, 4, 5, 6, so on the right diagonal. But the other numbers are obtained like in a Pascal's triangle. And then it is interesting to read this sequence this way, following the right diagonal, or also we can read it this way, following the left diagonal. So in this lemma, we actually prove that we do get a Pascal's triangle. It's elementary computation. And then when we read it the other way, again, we get some sequences that we can find in the encyclopedia, but not with the interpretation that we have. Okay, so now let me show you what is this online encyclopedia of integer sequences. Probably many of you. Rocco, have you seen that before?
I'm sorry, repeat your question, please, Professor.
Have you seen the online encyclopedia of integer sequences?
I have. I think Professor Prodinger introduced it last year somewhere.
Okay, great. So this looks like this. You can just search online encyclopedia for integer sequences. And when you type a sequence here, and let's type a sequence from these things. So let's go back to the number of partial symmetries of a cycle. So these are the numbers: 2, 7, 22, 61, 181, 571. By the way, we confirmed these numbers not just by making sure the mathematical proof doesn't have a mistake, but we also wrote a code separately to count these from scratch without using our formula. And then the answers matched. It's actually a useful tool for confirming if there is maybe a slight error in that binomial formula. So if we search that, you see nothing comes out. If I take off the last number and I search that, still nothing comes out. if I do this one more time, then something comes out. Okay. All right, now let's go back to our Pascal's triangle. And let's search for, let's say this one, 3, 2, 7, 16, 30, 50. 2, 7, 16, 30, 50. There we go. We even have a nice formula for this. And what we see here is a description of this sequence in different ways. So these are different combinatorial interpretations of this sequence. And you see one of them is the one we talked about, the number of inscribable triangles within an n plus 4 gon, sharing with them its vertices but not its sides. So when j is equal to I, these numbers are indeed known. But when we change dependence of j and I, then not. Okay. And then we have different ways of interpreting this combinatorially. So this is just one way, but there are also others. And then also each entry gives references where you can read up on this a bit more, and some links, online links. Then there is some discussion on formulas and so on and so forth. So it's a very nice thing, this online encyclopedia, because you can look at some discrete structure, play with it, get some sequence out of it, and then see if the world knows the sequence or not. And if the world does, then you can learn about this sequence. And if it doesn't, then you can do research and eventually contribute yourself and propose an entry in the encyclopedia. Okay, so we are coming to an end of the talk. I'll just gather my thoughts to see if I said everything I want to say. One last thing I wanted to show you, very much work in progress. So what I did is what we did was that we also counted this number for not for cycles but for paths. And then, so we got a nice formula. That's also something that Francois solved originally. And then I wondered what will happen if I have double-sided arrows. So this means that in this directed graph, we also have arrows going backwards, okay? Quite remarkably, these numbers are also unknown. And I want to ask you another question. So if there are 15 vertices like this, and there are double-sided arrows, what do you think, how big this number is going to be? Is it going to be million, 2 million, or 1,000 maybe? Can you give an estimate? So with n equals 15.
32,000.
32,000.
At least.
Okay, it's very interesting. So I'm going to show you now what the actual number is for that. So these are star graphs, and here we have chains. There we go. You said 32,000, right?
I've got a feeling I was wrong.
This number is so big, I even struggle to read what number it is. It's quite remarkable how numbers quickly get big. This is quite remarkable. But not just the number is big. Actually, the formula is also quite big. It took me a whole day to work this formula out, with the help of a computer confirming every time I made mistakes, because I usually make lots of calculation mistakes. You see how big the formula is. It stretches on 3 lines. Huh? Now, I showed this to my co-authors, so they were very excited about this. And then Francois said that maybe I can simplify your formula, and he's still working on it. So we will let you know if we can simplify the formula. Okay, so I think that I now reach the end of the talk. Thanks so much for your attention.